busy, you know, then you're not farming, blah, 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 blah. So he saw a need, created the very first AC buzz box, and that's what started the company. And then every farmer could afford these nice little buzz boxes, and they could do their own repairs at their farm without having to go into the expense of buying these great big generators. So that just started the company, and like I said, we have our main manufacturing facility is in Appleton, Wisconsin, almost downtown. It's 1 million square feet under one roof in downtown, and then we have we've outgrown that one several times, and so we have branched out. We own a lot of other areas that just kind of outside of Appleton, Wisconsin, but anything that says Miller on it, all of our Miller equipment is built right there in Wisconsin. So either Appleton or a surrounding city. As for Hobart Brothers actually started before that. They started in 1912. And they started by making generators, motors is what they started with. And then there was 3 brothers. That's why it was called Hobart Brothers for many years. Now it's just called Hobart Filler Metals. But back when it started, it was Hobart Brothers. So you had these 3 brothers, and they all specialized in different areas. One of them obviously broke into the filler metal division, and that's what it is today. We still own the other ones. The other one is ground power and transportation. So, anybody ever been on an airplane? Okay, yeah. When the airplane is sitting there at the gate, they don't have the engines running, right? But you still have air conditioning, you still have power to the jet. Well, those units that provide that are made by Hobart. And we actually build those in Florida. We don't make them all, there's other people that make them too, but we're probably about 60% of all ground power units are Hobart. So that's one division. The other division, anybody ever worked in a restaurant? Seen restaurant equipment? You might see a Hobart name on these great big mixers and slicers and stuff like that. That's actually another division. And yeah, we still own them, and they still produce those slicers and mixers. It's a huge part of the business. And then the part that I work with, of course, is the filler metals, and that's the other brother. So the brothers have long since passed, and company's been sold. The ITW bought Hobart Brothers in 1996, I think it was. I've been with Miller since 1995, so we bought Hobart the year after I started. That's kind of a quick history of the 2 companies. Obviously, anything that has to do with filler metals on the Hobart side and or power sources on the Miller side is what I deal with. I'm what they call a field application engineer, so I cover Utah, Nevada, Wyoming, and Colorado. And I work with end users, a lot of the larger end users, and I was once in your seat, not here at Weber State, but at Utah State, where Utah State used to have this program. So back in, I graduated in 94, and then worked for a year out in the field, and then started at Miller Electric a year after graduation, which was great. I happened to be working in Wheatland, Wyoming at a power plant out there. I was doing some welding out there, and that's where I had my interview with Miller. The truck stop is still there. I remember going in there early one morning and getting a phone interview, and then that was in October. Then November they flew me to Wisconsin, and that was the first time I'd ever flown in my life. I was a little bit nervous, but hey, it was pretty cool. And I walked into Miller, and I knew that's where I belonged. And thankfully, they offered me a job. Here we are, 26 or so years later, 25 and a half years later, and still love it. So good stuff. So anyway, I've been around a little bit. If you have questions, I'm going to mainly focus today on GMAW and more specifically 2 processes that you're going to run into that are fairly new, and that would be RMD and ProPulse or AccuPulse. It depends on what power source you're working with as to where you'll find the pulsing. And we're going to go over it a little bit here, and then we'll go out in the lab and I'll actually go through it on the equipment out there so you get to actually touch it, feel it, and weld it. Okay? So as you have questions, just holler at me, and we'll go through. I may ask you some questions, which is great, because you don't have to ask them all. But one more thing. Those of you that are, I talked to a couple of you guys already, but just an FYI, Miller is doing interviews on the 23rd of October. So if you're not signed up already, I don't know if there's any slots still open, but if there is, I would recommend jumping on it. if you have any inclination, even if you don't, at least it's good practice to know what you're gonna get into as far as interviewing. So, if you're gonna be graduating anywhere from now till probably within the next couple of years, really, please sign up.
Yeah, sign up online.
Yeah. Yep. So it's gonna be, I think we start at 10 o'clock. You looked at it, right? You remember what time we started? I think it was at 10 o'clock. I don't know. I'll be here. I'll be one of the interviewers. So if you happen to draw my short straw, then you might be in with me. We'll see how it goes. We're gonna have probably 4 guys here. So anyway, just keep that in mind. So I think we start at 10, and we break from noon to 1 for lunch, and then we start, and then we go from 1 to 5, I believe is what the schedule is.
What's the interview for?
For positions at Miller.
Like all sorts of positions or specifically which ones?
All sorts of positions, but mainly, obviously, being that you're in this degree program, we're focusing on welding engineer. But depending on where you are within Miller Electric, a welding engineer has a different job, right? If you're a welding engineer at Miller Electric, you're going to be responsible for producing and helping engineer new equipment, new technologies. It's the best freaking job in the world. I loved it. Anybody ever welded with a Dynasty out here? Yeah, you know what the Dynasty is. Okay, that's my baby right there. I was a weld engineer on the Dynasties. Obviously, they've gone through a lot of changes since I first did it, but the Dynasty was my baby. That was one of my projects. Bobcat was another project. Maxtron was another project. 60M was another project. I mean, you get a lot of behind the scenes. So you'll be welding with equipment that doesn't even have a name yet, right? And that's part of being a welding engineer. Is you're working with design engineers, mechanical engineers, and electrical engineers. It's a team effort. We don't just throw you in there and say, hey, make the machine. No, that's not how it works. So it's a collective collaboration, trying to get this stuff figured out. But you'll be welding with it. The Dynasty that I welded in was mounted on a piece of plywood, about the size of that table. Had all the different components, all the components that you guys have learned about, transformers, rectifiers, SCRs. I mean, anything that you're dealing with, it's all mounted out here, and it's pretty much out in the open, and you're welding with it. Because we don't want to make a machine until we know it welds good. And then that's when the design engineers come in and say, all right, we're going to put this here, we're going to mount this here, we're going to put this here, the board's going to go here, blah, 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 blah. Okay. So that's one part of being a welding engineer. My job as a field welding engineer is I actually help our customers figure out how to weld their more of their technical projects. So you never know what I'm going to run into. If I happen to walk into let's see, just thinking of an example. Some of you may have heard of Blue Star Steel down in Salt Lake. Tech Steel is another one. SME is another one. Those are the kinds of companies that I work with, and they'll call me up and say, hey, I heard about this R&D. We're going to talk about R&D here, right? I heard about this R&D. Is it any good? Well, of course it's good. You bet it is. So I go in, I visit with them, I look at their operation and see how R&D can benefit them. I'm the kind of guy that if it's going to benefit them, I'm going to show them how, I'm going to prove it to them, and I'm going to work with them and train their guys and help them be successful, right? If I don't think it's of any value to their organization, I'm going to tell them straight up. Say, you know what, I'd love to sell you a machine, because that's what the DMs do, the district manager. He's the sales guy. He's one that sells it more or less, and I'm the one that makes it work. Kind of. That's how I explain the difference between our roles. But if I don't think it's going to help them at all, I'll tell them straight out. You know what? Keep doing what you're doing, or maybe look at this power source instead of this one. Maybe this is the one that you need. You're looking for power source or power efficiencies. The machines that we produce today are much more efficient than the ones that were 30 years ago. I'm working with a company right now. They're replacing 50-year-old machines. I think there's a difference between the 50-year-old machines and the ones produced today. Huge difference, huge. Yeah. They're going to save quite a bit of money. They'll probably pay for that equipment in the course of 2 years just in power consumption savings alone. Yeah, question.
So, based on your job description, is it correct to assume that you have all of the certifications, like welding certifications and operations?
So that's a very good question. How many welding certifications are there? Yes, exactly. Hundreds, maybe thousands. You know, realistic, I am a CWI. I'm a certified welding inspector, I'm a certified welding educator, and I'm a certified welding supervisor, all from the American Welding Society. So I hold those certifications, those credentials. Yes, I am a certified welder, but what does a certified welder mean? I could make every one of you guys a certified welder today. If I wanted to certify you with bead on plate, you'd be a certified welder. And I guarantee you can pass that test today. Okay? Even if you've never struck an arc before in your life, I could probably get you doing that in an hour, right? So certifications are important, but they are very job specific. Before I came to work at Miller Electric, I was a certified pipe welder. Okay, so I worked for a company called Brown Minneapolis Tank. You maybe remember them. They're no longer. Actually, I think they changed their name a little bit and then kind of come back on. But back then, this was back in the early '90s. But Brown Minneapolis Tank, I was their pipe welder. They built these tanks, and I would do all the piping that would come off of these big tanks for fire suppression and things like that. Guess what? I was certified, right? I held the certification for that. But when we went from a job in Oxnard, California to a job in Wheatland, Wyoming, that's the company I was working with, I show up on the job, first thing they do is roll out the leads, and guess what I had to do? Test. Yep, I had to prove myself for that job. Even though I was still working for the same company, doing the exact same job, I still had to certify. And if I happen to have a bad day and fail, well, see you later. You know, they'd let you test a month later. I could come back and try again. Luckily, I never failed that certification. So, certifications are important, but they're very job specific. And if you want to be a certified welder, that's great, but just keep in mind, if you're a certified welder, you walk into a place and you show your certification, the guy's gonna look at that and go, hey, that's pretty cool, prove it, right? So it's not just a one and done, you gotta keep your hand in it. If I were to try to pass one of those certifications that I used to do, it might be a struggle for me today, right? Because that was quite a while ago. Not that I don't weld, I certainly do, but I don't weld to certification levels on pipe anymore. Now, if I had my RMD, which we're going to talk about here in a little bit, I could do it easy. Piece of cake. And I'll show you why here in a little bit. All right, any other questions? What do I do with my clicker? I'll separate that. Okay. So GMAW is a topic, and we're gonna dive down to the different modes of transfer. Is really what I want to talk about while we're in here. First off, this is just a kind of a quick diagram of a gas metal arc welding system. Just out of curiosity, what is the very first thing you need to put together this system? It's all on board there, but what's the very first thing you need to put together a GMAW system?
Money.
Money is very important. Yeah. But what's the first thing?
Power source.
So when we say power source, we're talking about the welding machine, right? Okay. That's a very good one. You gotta have it, otherwise you can't weld. But what's the first thing you gotta have? Electricity. Yeah, that's important. Otherwise you can't plug this into anything, right? Some people call that the power source. Just know in the welding industry, when we refer to a power source, that is the welding machine. When we talk about a welder, that's you. Okay? So, just terminologies, they might mean a little bit different thing in different industries. But, so electricity, again, very, very important. But what's the very first thing we gotta have?
Place to put it.
Good place to put it. Yeah, that's
I need to use it. I need to use it.
What's that?
I need to use it.
There you go. Hear what he said? This thing right down here. That is the most important thing in this whole setup right here. Yeah, you've got to have money, but if you don't have this, it doesn't matter what money you have because it doesn't mean anything. You need a power source, you need a wire feeder, you need your gas cooling system is optional depending on what you're working on. All this kind of stuff, but this work right here is going to dictate what you need here. Because isn't a wire feeder, that picture over here on the sidewall, we've got a couple of different machines kind of floating around. If you look in the right hand lower corner, this right here, that's called a Millermatic 150 is what that says. That's a real nice home hobby machine. Is it a GMAW machine? By the way, anything that says Millermatic is GMAW. So, is that a GMAW machine? Mm-hmm. Absolutely. It's a great little one. Would I weld buildings together, skyscrapers? Would I weld bridges with that? No. But then I've got another machine up here. This is called an XMT 350. Is that a GMAW machine?
Can be.
By the way, all XMTs can be GMAWs. They can also stake a TIG as well. But they are GMAW. Now, am I going to be building buildings, bridges, stuff with that machine? Absolutely. You betcha. They're done all over the world with that machine. But they're both Gassman Lark's welding systems. So what's the difference? The difference is the work, right? If I'm going to have something in my garage and I'm doing auto body stuff, just like it kind of shows in the picture, it's a great machine, you bet. But I can't do the heavier stuff with it. Now the XMT up there, notice he's welding pipe up there. Will it do that? Absolutely. It does a great job on pipe. Could you weld auto body with it? You betcha. It does a great job. It's got a super art. But I'm probably not going to dump $15,000 on a system when I can get one that'll do my auto body for about 800 bucks, right? So work is extremely important. As a welding engineer, that is one of the biggest things I hope you will learn, is to identify the work. There are several questions when somebody asks me, what machine should I buy? What do you think the first question is going to be? What are you doing with it? Absolutely, right? What are you working on? Then what am I going to ask? Not yet. Because I'm going to let the work dictate the process, right? Do I have enough information? By saying, what do you weld on?
What's your budget?
Not yet. That's a good question. Yes, we got to ask that, but not yet.
Material type?
Material type, thank you. Now, sometimes you'll get that by asking, what are you working on? Sometimes they'll just, go ahead and spout that off. But if they don't, yes, you've got to ask that question. What type of material? Is it steel? Is it stainless? Is it aluminum? What is it, right? Is it Inconel? Is it a Monel? What is it? We need to know that, okay? And then the next one, there's those three real important ones, and this is all pertaining to the work. What's a follow-up to? What type is it? How about how thick is it? That is going to determine, right? Because if I'm welding 1 inch thick plate steel, I'm probably not going to be very successful using a 150 amp machine. I'm not going to be successful. I'll just tell you that. You will not get her done. Yes?
Wouldn't where you're welding it at also be kind of important too, because you're working
Absolutely.
outside?
Absolutely. You bet. So we've asked those three basic questions, right? What are you welding? What type of material is it? How thick is it? Now another one would be, where are you doing it? Are you doing it outside? Are you doing it in a shop? And that's going to dictate also what kind of filler metal you're going to need, right? Because if I'm doing it outside, what do I not want to probably be running? Gas. Yeah. Unless you build a tent over it, and block the wind, but sometimes it's feasible, sometimes it's not. Anyway, so this work will dictate, though, everything that goes into this welding system. So those are some of the things that you need to learn, and learn that really early, as soon as you can. Everybody's got at least a year yet, right? Maybe a little less, but a year left of school. So that's the part right there that's really going to impress even some of your interviewers too, especially at Miller Electric, if those questions ever come up. Because that's really the bottom line. You can't help somebody unless you know what they're doing, right? We get questions all the time. When I say we, I mean myself, other engineers in the company. We get questions, hey, I'm welding steel. What do you recommend to weld it with? How thick is it? I don't know. What grade of steel is it? I don't know. Well, as soon as you find out, call me back. Because otherwise I can say, well, I've got a list this long of filler metals. Use one of those. Here you go. Right? Yeah. It's just dive down, get it figured out. The work is even going to dictate what the size of lead you're going to be using. Because if I'm welding some heavier stuff, I'm going to need a bigger power source. I get a bigger power source, I need a bigger lead. Right? Don't discount the lead. But I will say this, if you don't know, go at least 4 off. It will help you. I've seen little tiny, little thin stuff be affected by having the wrong work leads and electrode leads. A lot of times, it doesn't matter. We always think of it as a high amperage, but even low amperage can be affected by it. Especially with some of these newer processes like the RMD, not so much, but definitely the pulse. It'll definitely be. I hate having to take a mask off just to have a break. I saw a mask online the other day. The guy was smoking a cigarette through it. Had a mask on, but he cut a hole in it so he could smoke. That's really? Okay, so let's run through the modes of transfer real quick. How many modes of transfer are there in GMAW? How many?
Three.
I hear a 3, I hear a 4. How many say 3? How many say 4? How many don't give a crap? Well, what is it? 3 or 4? Maybe there's 5, maybe 10, right? No, there are 4 modes of transfer. Okay, just so you know. We're going to go through real quick because we're going to focus on 2. These are the 4 right here. Short circuit, globular, spray transfer, and pulse spray transfer. Now, technically, if you look at the transfer side, spray transfer and spray transfer, right? The difference between this is how we get there. Here we're using pulse equipment, here we do not. But there's still spray transfer, but according to the American Wellness Society, they do deem them as their own individual type of transfer, okay? The big difference between the spray transfer and a pulse spray transfer is the size and number of droplets. The spray transfer is going to be continuous. So these little droplets that are coming across the arc. When we talk about transfer, it's the transfer from a solid state in your wire to another solid state in your well. So this is your molten state in between, right? That's the transfer, how we transfer it from the wire to the material or to the well. So in spray transfer, you have a whole bunch of tiny little droplets that come across there at a very even time and space. We can't see it unless you have some high-speed video equipment. Then you can't see it, and it looks way cool when you watch it in a high-speed video. Man, it's way cool watching it. But just welding, you can't see it. Once in a while, you can kind of get a look at it on the pulse spray. So again, the difference here, continuous on the pulse spray. The only time that you have a transfer is at the peak amperage of the pulse. The background amperage is low enough that there's no transfer across the arc. Okay? And so with that difference, again, the AWS has deemed it as his own individual transfer process. So let's run through all these real quick. The video link is bad, so the short circuit transfer, what's it good for? Thin material out of position over or fill. That's kind of what short circuit is good for, right? What's thin material? Okay, I hear a sheet, I hear 3/16. What's thin material to you?
Anything for lower?
Okay, what's thin material to you? 3/16. What's thin material to you? 1/16. So there's a little bit of difference going on here, right? You talk to an iron worker, 1/2 inch plates, thin material. Okay, so it's all relative, right? So let's think about it just for a minute. Thin material, what are we talking about? What we're talking about here, short circuit process, is 1/4 inch or under. Okay, 1/4 inch is really the max. 3/16 is probably better, but 1/4 inch is your max, and everything's got to be just right, otherwise you can run into lack of fusion really easy. And that is why, this is a huge misconception in the welding world, but that is why people think GMAW is not as strong as stick. You ever heard that? I guarantee you will hear that. Let's look at this real quick though. What wire are we typically using in GMAW? What is the most common wire? ER70S-6, right? What is the most common stick electrode? Number 1 electrode sold in the world. 7018. What diameter, by the way? 1/8 inch. That is the most common stick electrode. This is the most common wire. So break them down real quick. What is the tensile strength of the 7018? Okay. Take this, right? So the key is it's a minimum 70K, right? Minimum. Then we know it's an all position, and then the chemical composition, right? So let's break this one down. What is the tensile strength of an EAR 70S-6? Minimum 70K. So which one is stronger? If they're welded correctly, they're equal. Okay? You can get this, there's some other designations here. They've got like an H4, could be an H8, even an H16. Okay? That's a hydrogen level. So which one is the best? Doesn't matter which one's the best though. What does it mean? What's that H4, H8, or H16 mean to start with?
How much water per humidity running the
So it is a moisture. It is moisture. It is hydrogen. That's what that stands for. But it's not in the rod. That's what a lot of people, and I get this a lot because you'll see this on an electrode. They'll be, oh, H4, it means I can have it out of the oven for 4 hours. I can have it out of the oven for 8 hours, or I can have it out of the oven for 16 hours. Has nothing to do with that, guys. What this is an H4 means there will be less than 4 milliliters per 100 grams of weld metal deposited. So this is after you have done the weld. You have produced the weld and you measure 100 grams of weld metal, there will be less than 4 milliliters of hydrogen in that weld. Here, less than 8. Here, less than 16. There's not a designation higher because who cares after that, really? So, which one would be better? Which one would you rather have? Number one cause of cracks is hydrogen. So which one would you rather have? H4, you betcha. I don't care what you're welding. I'd rather have an H4. Just for, so why is there a difference? Why doesn't everybody just make an H4? Well, because typically as you go higher or lower in this number, weldability goes down. Okay? And there are some manufacturers that can't seem to produce a good running electrode with an H4. Ours, by the way, our 418, the most common, the best running 7018 ever is an H4. And it will compete with any H8 or any H16 of other manufacturers. Now, I'm going to get, I saw a hand up, so I'm going to get there, but I want to finish this point. H4, very good, right? 4 milliliters per 100 grams. What do you think the rating is on an S6 wire? Solid wire. It's always an H4. Always. There is no other rating other than H4 because solid wire always beats an H4. So the reason I bring that up is because that's also a measurement of strength. How much hydrogen is in that weld metal deposit, right? So when you're looking at this, 70K, H4, 70K, H4, again, if they are welded correctly, they are equal in strength. The reason GMAW gets a bad name is because of short circuit and people trying to weld too thick of stuff with the wrong mode of transfer. Even though if they understood there are other modes of transfer and all it is a setting on their machine to turn it up and to make it correct, to do the job correct, they would never have it run in that problem. Yes.
You might have said it, I just might have missed it. The most popular size 7018 is 1/8. What's the most popular size wire for E7?
This would be 0.035. Yes. A close second is 0.45. That's for manufacturing. But as a whole, we make a lot more 0.35 wire than anything else. The 0.45 wire is a close second. All right. So let's move on to our. We kind of talked about this and the limitations. Well, let's talk about this around here first. Limited use on aluminum. I would like to amend that and say never use it on aluminum. Okay? Never use short circuit on aluminum. Believe it or not, you can use a spray, you can get into a spray transfer with small diameter wire on aluminum and do 1/8" aluminum. You can even do 1/16 aluminum in a spray transfer. It does not follow the same rules that steel does. Okay? So never, and the reason we don't short circuit on aluminum is because you're already having a hard time keeping the porosity out of aluminum, even in a spray mode. It's very difficult to get a porosity-free aluminum weld. If you use short circuit on aluminum, you are guaranteed that thing's gonna look like Swiss cheese inside. Guaranteed. Okay, globular transfer. This is one that we don't even really recommend, but it is a very common process because people don't know what they are, what it is. And guys will think that they're running short circuit, they're running this wire, think they're running short circuit, and then they just crank it up and think they're still running short circuit. No, it's not. What is the most common gas that we use for this wire? Which is, C25 is correct, but what is it?
25% CO2 and 75% argon.
Okay, in the welding world, we always do the larger amount first, right? So, 75% argon, 25% CO2, that is the most common. So, if I were to walk into a shop and let's say I'm running at 23 volts and I'm running, let's say 350 inches per minute with the most common size wire, 035, what mode of transfer am I in? Are you sure? Are you sure, or are you probably sure?
If they're running 100% CO2, then guaranteed, I would say it's getting.
We're running 75-25 with 035.
I would say it's a globular transfer.
Anybody want to dispute or agree? Not really. No, yeah, whatever he said, that's good. We're good with that. Yeah, that's awesome. But you are correct, and I'm glad you finally settled in on it. I guarantee you that's a globular mode transfer right there. If you're at 23 volts, you're a globular. Short circuit is good up to about 22 volts. You can't start spray until you hit 24 volts, and that's only if you have the right gas. Even if you're running 75-25, you'll never get into a true spray. And then a lot of people call it a modified spray. Well, guess what? We already have a name for that. It's called globular. Okay? So if you're not in a spray, you're not in a short circuit, you're in globular. And that's why globular is used so much, is because any mistake that you make in setting your parameters will wind you up in globular. And yes, you can even pulse globular well. Because if you screw up your settings in pulsing, you're still going to get a globular transfer. Okay? Just because you're pulsing does not guarantee that you're spraying. So keep that in mind. So your transition, it's kind of a transition. We don't have that on here, but the transition from short circuit to spray, and that transition happens from around 22 volts to around 24 volts. So if I'm at 23 volts, I'm guaranteed I'm in a globular transfer. Okay? It's going to happen. Okay, spray transfer, advantages there. High deposition, good fusion penetration, because we're running some higher amperages, right? We're at higher heat, higher voltages. Because of that, you get good bead appearance. You can use larger diameter wires. In fact, most people that are using the spray are using larger diameter wires, 045, 052, even 1/16 wires, and they're really hogging it in there. Most people that are using 035 wire don't necessarily jump into a spray transfer, because then their wire feed speeds have to go so high that it's not feasible a lot of times. There shouldn't be any spatter, a little bit maybe at the start. This is a non-contact type of process. In other words, the wire touches once to get the arc started, and then after that the wire never touches the base metal again. Whereas with short circuiting and globular, it will touch. With short circuiting, it touches about 25 to 250 times a second, okay, depending on your other settings of the machine. With globular, it's hit and miss. That's why it's globular. Sometimes it'll come down, big explosion. Other times it'll weld really nice, and then other times it'll come down, but there's no rhyme or reason. There's no consistency to it. With spray, very consistent, as in the wire does not touch the basement. Okay? All right. Limitations, yes, we can't use it on thin material because it's so hot. Really, 1/8 inch, you better have everything just dead nuts on, otherwise you're going to blow through 1/8 inch real easy. But typically, if you're doing 1/8 inch, you're more than likely you're doing spray now, or pulse spray nowadays. Says here works best in the flat and horizontal position. No, it works only in the flat and horizontal position. I'll challenge any of you to go out there, set it up for spray, and do a vertical for me. Do a vertical up. I'd love to see that. You got a trowel, help it well, and kind of trowel it up, there you go. It's so molten, it's not gonna go very well. Okay, so the good stuff, let's get to our pulse spray transfer. The advantages, all position, meaning, if you think about the other modes of transfer, we've got our short circuit, globular, and our spray. Which one of those three modes of transfer, the short circuit, globular, or spray, allow you to do all position? Short circuit, that's it, right? Okay, no spatter. Which one of those three, short circuit, globular, or spray, gives you no spatter? Spray, very good. Thin or thick materials, short circuit, globular, or spray, which one of those allows you to do thin to thick materials? None of them. Spray is good for the thicker materials, short circuit is good for the thinner materials. So to keep it maybe straight in your mind, just think of short circuit up to quarter inch. Quarter inch and above, spray. Pulse, however, allows you to do it all. So as you can see, that's why so many people are turning to pulse MIG welding, is because it takes the good things of short circuiting, the good things of spray arc, and you can do it all, thin or thick materials with a pulse spray. Now there are still some places where short circuit is shines. There are still places where just good old GMAW spray transfer is going to shine where pulse is not needed. But most of the time, spray is going to become a benefit. It gives you extreme flexibility and productivity because of this, and the programmability to do just about anything you want with it. And that really just depends on the level of power source that you purchase. The one power source we're going to go over out there is called the continuum. Anybody messed with the continuum yet? Okay, a little bit, good. There's a lot of crap in there, right? If you turn that on, holy cow, there's menu behind menu upon menu upon, there's all kinds of stuff in there. It's awesome. And that's just the tip of the iceberg. That machine also has what we call web pages. So I did connect it at one time, but for some reason I haven't had time to reconnect it. But I can jump on right here, or with my smartphone, anything that has the ability to get to the internet, and I can dial up web pages, and I can dial in that machine from my phone, from my computer. If that doesn't work for you, you got an Ethernet cable, plug it into the machine, and you can do it all right there on your laptop. So a lot of sophistication, right? Then we have, over in one of the other corners, an MPA, XMP MPA. You guys welded with those? Hopefully you have, as I think everybody did, at least in the beginning welding classes here, right? So those still has ability to pulse, but the programmability is very minor. There's very little that you can change in that machine. There are some things you can change, but nothing compared to the computer. Okay? And then we have, we have some rubber ones even in that will get you the pulse. Somewhat. Not so much on the pulsing side, but there are some programs like you can do sequencing with it. You still have the ability to do the arc length adjustability, which does change things internally. But as far as something like a continuum, no, not even close. But that's a great entry-level machine for someone in a garage or something that wants to get into pulsing. That's the very first ever 250 amp pulse machine. And every time I weld it, I get more impressed with that arc. It's got a great arc, especially on the pulse side. Okay, so some other advantages of pulse spray that aren't necessarily on this list. Let's see if there's another list. Nope, fume. What is the number one element in the fume that comes off your weld? Anytime you strike an arc, you have fumes that come off, right? Some processes produce more fume than other processes. GMAW is going to be one of the lower ones. Pulse GMAW is going to be the lowest as far as a GMAW process. So what's the number one? And again, we're just talking about GMAW. We're using a solid wire. That's what that S stands for, right? It's a solid wire. So we're using a solid wire. Still going to produce fume. What's the number one element in that fume? grinds with iron. It is iron. Okay, it is iron. That is the number one element that is in that plume of smoke coming off of your well. But where do you want the iron? I want it in the well, right? Pulsed MIG welding allows you to do that. Because of this, the background portion, you have a peak which transfers the filler metal across the arc. You have a background which kind of allows that puddle to cool slightly. And because of that, we get less fume. That iron stays in the part where it belongs. So that's another advantage, is the amount of fume that comes off there. The amount of heat that is generated will be less with pulse than it will with traditional spray. A lot less. So if I have less heat input into the part, what does that mean? What happens to steel when you put heat to it? It warps, absolutely. So if I put less heat into it, you're going to get less warpage, absolutely. Yeah, but there's a lot of guys that have gone to pulse MIG welding. Who cares about any of these benefits? They do it strictly for the amount of heat. Okay. Now, a nice thing that's on the continuum and on the delta weld that's out there is we actually give you the kilojoules per second of heat that you're putting into that part. So all you got to do is measure how long your part is, and boom, you know how much heat you put into your part. Makes it really, really simple. Especially if you get into, you know, the inspection part of things, welding engineering. Okay, let's see, was there any other advantages? Trying to think of. If something comes to me, if you guys have a question, then we'll talk. Okay, so now we're going to talk about RMB. Now RMB, why is it not classified as the fifth mode of transfer? That's because it's not a fifth mode of transfer. It actually falls under the short circuit mode of transfer. Okay? Basically what RMB stands for regulated metal deposition. That's what RMB stands for. So regulated metal deposition. The RMB, we call it Pro because it's in our pipe works, our pipe pro machines. It's also in the Access, it's also in the Continuum. So Pro is just the next generation, if you will. And the same with Pro Pulse. It's still a pulsing program, but if we call it Pro Pulse or AccuPulse, some of you may have heard of AccuPulse, those both mean the same thing. It just depends on what machine it's on. Like on the Pipeworks, it's Pro Pulse. On the Continuum, it's AccuPulse. Okay? So basically, again, what that is, it's the next generation of pulse. And we use a device net cable instead of just a regular 14-pin. And through that, we're able to get a lot faster communication between the power source and the wire feeder. Allows us to run tighter arc lengths, which means that we have more controllability from the welder standpoint. We can do higher travel speeds with it. So those are some of the advantages of the AccuPulse over traditional pulse. Okay? So RMB is a modified short circuit. It is recognized by the American Welding Society as a short circuit process. The reason that that is important is because there are a lot of pipe welding procedures out there that have been qualified with short circuit. The average cost to do a procedure is $5,000. So if I don't have to redo a procedure, requalify a procedure, guess what? I just saved $5 grand, right? Now some people do it in-house, so it's a lot less money. Maybe it's only $1,000 for a certain place, but either way, you're saving money. You don't have to re-qualify your procedure. So if you come in with a process that says RMD, hey, this is going to make it a lot easier for you to weld this pipe or this project, and really, it focuses a lot on pipe, but it's really for anything that is an open root. It doesn't matter if it's plate or what, okay? It works very, very nice. In fact, I think Jeff's going to have you guys do maybe some welding on some plate, just to experience the RMD. So that's its forte is root passes. So what I tell people is just remember RMD is for the root. That's what that R is for, right? Regulated metal deposition, but the R, remember, that's for your root. I get a lot of guys saying, well, what, can I just weld the whole thing in with that? Sure, you can, but why? If you have a machine that has RMD, you have a machine that has the pulse, and pulse is going to be way faster for doing the fill and cap passes on a pipe, okay? Or anything else, really. Okay, so RMD. Basically what we're talking about here, early prediction of the short. As you know, short circuiting, hopefully you know this by now, short circuiting, it's a four-step process, basically, where your wire comes down, it touches the base metal, that sends a signal to the power source that says, hey, we have a dead short here. You asked for 17 volts. Let's say, I asked for 17 volts. That's what you told that power source you needed, right? Well, as soon as it dead shorts, how much voltage do you have? 0, right? So that tells the machine, hey, wait a minute. You told me you wanted 17, so it's going to reach out. And what does it hit it with? Amperage. Amperage is what clears that short, not voltage, okay? Amperage always does the work. Just keep that in mind. Amperage always does the work. So it hits with a whole bunch of amperage to burn that off, and then all of a sudden it burns it off, and that starts up. So again, there's number 3 that burns that thing off, and then number 4 starts coming back down again. That's your 4-step process. R&D, we monitor what's going on at that arc all the time. With short circuiting, the type of gas, the diameter of wire, the type of machine, and the inductance in that machine will all dictate how often those shorts happen, okay? So it's kind of just hit or miss, really. There's no, I mean, there is science to it, but it's a combination of these 4 things. But what we do with the R&D is we monitor the arc. We monitor the arc 10,000 times a second. So we know what's happening at the arc when it's happening. That's what allows us to predict that short. So when that short starts to occur, instead of hitting it with all that amperage, let's say on a traditional machine it took 250 amps to break that or clear that short. With this one, we hit it with 250 amps, but as soon as it sees, because as soon as that starts to neck down, that wire starts to neck down, guess what? Your voltage starts to rise again, okay? And when the voltage, as soon as that starts to rise again, we go, hey, wait a minute, okay, it's going. So we take that amperage and we cut it back. So instead of a and spatter, we get a little tiny, if you will, spatter. It's not a huge violent thing, it's just very small. This is a 7-step process basically for R&D. Okay? Where it comes in, it touches right here, it feels, all right, we need some current, this is where it starts to ramp up, and then when it ramps up really quick at a steep angle, and then it kind of softens off. As soon as this thing starts to break, we go, wait a minute, boom, and we drop that current almost instantly. It's almost like choking it instantly, right? We drop that current down. We still maintain some current, but we keep it at a very low value, just enough to keep an arc on, and then we ramp it back up to give you the wetting effect that you're looking for, because you want that arc to wet out, right? And tie into the toes. We wet it out for a certain given amount of time. This is dictated by the amount of wire that you're putting into the part. So if I'm running at 350 inches a minute, then it's going to be more than if it was at 250 inches a minute, right? So we'll stay on longer. Once that predetermined amount of time happens, we bring it back down to what we call our background amperage, maintaining an arc with a very small one. And then this pre-short occurs. The pre-short is basically preheating the wire again so that we don't have an explosion over here. So there's your 7-step process of R&D. And we can do that because we're monitoring the arc all the time. Okay? And we do that through a sense lead. So the advantages of R&D Pro, we get very good sidewall fusion, less, if not any, weld spatter, which in short circuiting you will get weld spatter, but not on this particular one. High-low, pipe is round, right? Right, Jeff? All pipe is exactly round, right? Yeah, well, we think of it as round, right?
Roundish.
But it's kind of egg-shaped, and then you have one's more round than the next one, so you get this, we call it this high-low situation going on, where they just don't exactly fit. So with your stick welding, TIG welding, it's not a big issue. With stick welding, you have to know what you're doing to make sure you capture both sides. You can't just burn it right in the center of the joint. However, with R&D, that's exactly what you do. You don't play favoritism to either one side or the other. You just hold it right there at the center of that joint. You trust the process and you drag it. That's the other thing with R&D. You always use a drag technique. All the GMAW use a push technique for the most part. Very seldom you do a drag. But with R&D, you want to do a drag technique. So all that equates to less weld repairs. If you have less weld repairs, it makes the boss more money. If you can make the boss more money, guess what? He rewards you by giving you more money, and you keep a job. It's kind of nice, right? All right. More advantages. The stable weld process, the state, I couldn't find the video, but it's on our website. If you want to jump on rollweld.com and check out R&D, there's a video in there that shows the backside weld of an R&D versus a short circuit. And you'll see on the short circuit, very violent, spatter coming off all over the place. It's a high-speed video, so it gives you a really good close-up. But the one with the R&D, you can hardly tell anything's going on. You see little ripples go out through the molten puddle, which is way cool. It's very, very calm, which allows, again, better operator controllability and better fusion into the sidewalls. Tolerant of tip to work distance. In other words, not everybody's really steady. Not everybody's steady Freddy, right? So you're gonna pull that gun away or put it in close. Again, we're monitoring that arc, so it doesn't matter if you're running really, really tight or if you pull up, you can be 2 inches away. As long as you have gas coverage, it'll still weld. It'll still do a great job. Which all that equates to less welder training time. In fact, if you have never welded pipe, in fact I did this right out here, this was a little while ago, I had a couple gentlemen come in because they wanted to check out R&D. Hey man, that R&D, that sounds great. We want to check it out. So we had one guy that came in, he was a 25, 30-year veteran of pipe welding. He'd never welded with wire before, but he was a good hand, right? He knew how to weld pipe. Then we had the gentleman they brought with him was a little bit younger guy. He'd only been in the business probably, say 5 to 10 years. Never welded pipe before in his life. In less than 2 hours, the guy that never welded pipe before in his life was spanking the guy that had all the experience with R&D. Why? It's because the guy with all the experience was trying to use that experience and equate it to this new process. So he was having to unlearn those habits, which work great for stick welding, but do not work with R&D. So that is kind of it's a challenge for some people, right? Because there's new stuff out there all the time, and there's a new way of doing it. And so finally, what I just told the gentleman, I said, you know what, you're doing a great job, but I can see you're struggling because you're using your experience. I said, what I want you to do, if you can, is just think back to the first time you struck an arc. Because the first time you struck an arc, you sucked at it. Nobody just lit up an arc and was the best welder in the world, right? It took practice to get to wherever they're at. And I said, if you can think back to that point, that's how I want you to attack this R&D, And it's hard to do, right? But he was able to be successful after that. So, very, very minimal welding training time. This is showing you sidewall fusion here. Everybody talks about pipe welding. They talk about doing a root pass, hot pass, fill pass, cap pass, right? That's your norm. When you use this process, you can eliminate a hot pass. Most people think that a hot pass is when you put the root pass in, then the next pass has got to be hotter. So you crank up your machine. That's how you run a hot pass. That is incorrect. Not that it can't be done that way, it certainly can, but that's not the definition of a hot pass. The definition of a hot pass means that you're on this weld before it cools. It remains hot to put the next pass in. So you do the root, you chip it, clean it, and give it right back on. Okay, do a hot pass. If you're using the RMD, we can eliminate that pass. At a minimum, I can, on any size pipe, I can eliminate at least one pass around that pipe. Most of the time, like if I'm on a 10, 12 inch pipe, which is really, really common, if I'm on one of those types, I can eliminate probably 3 passes. If you go to an RMD and a Pro Pulse, eliminate 3 passes. So if you eliminate 3 passes, how much time is that? That's a lot of time, right? So on average, a 10-inch pipe, we will save $15 per joint. On average. That's not even using the Pro Pulse, that's just using R&D. But we'll save at least $15 per joint. You start thinking about that, how many joints go into a piece of pipe, when you keep on going. It adds up really quick. This one right here says eliminates the backing gas in some stainless steel applications. It can eliminate it on all stainless steel applications if a person is willing to re-qualify the procedure. Okay. You can get enough backing gas through the joint that actually goes through because that RMD puddle is so calm, the gas that goes through the joint actually protects the back of that joint and it cools before that gas is gone. Okay. But it does, you do have to, because you changed the essential variable, you do have to re-qualify the procedure. So some people choose not to do that because of the cost of re-qualifying the procedure, right? So, and that's okay. The gas guys love it, keep purging it, that's fine. The gas guys love it. This is an example of the high-low. You can see the ruler right here. You get the high-low. This is the inside of the pipe. It doesn't care. You hold it right in the center of the joint. It's going to give you a beautiful, beautiful bead. Okay? Pro pulse, we kind of talked about the advantages of pulse. The pro pulse just helps in the fusion and fill the toes of the well, so then you do a tighter arc length, so it allows you to manipulate a little bit easier from an operator standpoint. We talked about the less heat, right? Less warpage, that is true. The nice thing, if you're to use the Pro Pulse in conjunction with R&D, you can actually do one wire from the root to the cap. So again, that takes less time to change over and go from one to the other. We talked about all that already. This is an example. This is on a 12-inch schedule 40 vertical up. So we do the Pro Pulse goes vertical up. So you go R&D down and the pulse up. There's pulsing available for, steel, stainless, chrome, duplex, just about anything out there, aluminum of course, but this is kind of a pipe program, so you much pipe welding for aluminum. If for some reason, more than likely we have a program for everything you're welding already. But if you happen to run into something that we don't have a program for already, all you need to do, this is a beautiful thing of working with Miller Electric, is you call us. You guys realize that you can call Miller Electric and actually talk to a human being right now. If you call up our any of our numbers, 920-735-4500, that's our service line, a person is going to answer the phone. Okay, still today. Now we do have somewhat of a little tree in there somewhere, I don't remember which number you call, but that'll just get you to the right area, like if you want service or machine sales or apparel or something like that, then you're going to get that and you direct it, and somebody answers the phone. If you do that, you can call Miller Electric and say, look, I'm welding this to this. Do you have a program? And if we don't have it, we can develop it. And we'll develop it, and then we'll save it on a thumb drive and mail it to you. You can download it into your machine, and or we'll email it to you if it's not too big of a file. We'll email it to you, and you can download it into your welding machine. As long as the welding machine that you're using allows the download. And that's the, those are the, I think probably our cheapest one is about 10 grand and lower. Okay, we're talking a little bit about gases, and I think that's it for the class time. Chilling gases. There's a lot of different chilling gases out there. These are just the most common ones right here. And this is just pertaining to carbon steel. So we have 100% argon, 75-25, 80-20. And then we have an argon 2% or 5% oxygen, argon 15, 5% CO2. So what this chart is saying is that either it's recommended, it can do it, or it's not recommended. That's basically what we're looking at. So we talked about short circuit, RND, globular spray, and pulse spray transfer. So as you can see, if I want to use 100% CO2 or 75-25, am I going to be spray or pulse spray MIG welding? Can't hear your head rattle.
Neither.
Right. Neither. Not recommended, right? Why? It's always important to know this, but then somebody's looking at, well, how come? You guys tell me, why? That is true, that it does give you a harder arc, but that doesn't explain why. Why is it a harder arc? Answer that, then you'll be on the track. Okay, you've been silent long enough. The reason it goes to is the ionization potential of the gas. What's the difference, what's the fundamental difference between argon and CO2? You have inert gases and active gases, right? So which one's an inert gas? Argon. What is CO2?
Active.
That's definitely an active gas, right? So the ionization potential of argon is much, much greater than CO2. When you go into CO2, because it's an active gas, it means if you apply heat, it's going to create an action, a reaction, right? So the reason we cannot use it is because if I need a minimum, if you look down here, next one down, I need a minimum of 80% argon in order to hit that ionization potential to create a spray arc. Has nothing to do with the pulsing of it, it has to do with the ability to spray that metal across the arc. Okay? So we need that ionization potential of the minimum of 80% argon. Again, I have a lot of people that run 75-25 and say, oh yeah, we run a modified spray. Yep, and it's called globular. Yep, we understand that. It's right there. Okay? And yes, you can do that. You can even run globular with that special no gas. You guys, anybody ever forget to turn the gas on and put a weld? Still welds, right? Still puts some bead of sorts down. It's full of holes, right? But you're in the globular mode because you made a mistake. Any mistake in any of your parameters will wind you up into that globular mode. So your short circuit window of operation is about like this. Your spray is about like this. Whole spray is like this. Globular is like this. Any mistake will end you up in that globular mode. All right, so the most common gases for our pulse spray, it would be in this category right here, 90-10. So this is anywhere from 15 to 5% CO2, but 90-10 is the most common across the U.S. There are pockets that use a 95-5, just because that's what the suppliers have always pushed, you know, type of a thing. But your most common is going to be 90-10. The nice thing about 90-10 gas is that not only can I do my spray, my pulse spray, and my spray, is that I can do all these other processes too. Now keep in mind, when you get into a 90-10, globular right there, that window of operation is still huge. RMD actually works very, very good. But on the short circuit, your window of operation, your voltage window gets really small. You can still achieve a short circuit, but it's not going to be a very good window to achieve that. Yes, sir.
I don't know, maybe you're going to cover it, but can you talk to us about costs of these gases?
So typically people that are looking to save money, they want to go with CO2, right? Because it's really cheap. And the reason it's so cheap is because it's so readily available. And it does work. If you're in your garage and all you're doing is 3/16 inch thick material and less, I would stick with the CO2. In fact, on my little guy at home, I've got a couple of welding machines, believe it or not. But on my little one, that's all I run is 100% CO2. Because I know I'm not welding any of the big stuff. As soon as you get into that 3/16, that 1/4 inch, I guarantee you're going to be globular by the time you turn it up to do 1/4 inch. And it's going to be ugly and nasty with 100% CO2, right? But I can still maintain a short circuit on that thinner material. And it works great. So in that particular situation, if you're going to have a home hobby machine, go with the CO2, especially if it's a 115 volt machine, because you don't have enough power there to get into globular anyway, right? So stick with the CO2, it's nice and cheap. But in manufacturing, I guarantee you, people are not using CO2 because of the limitations. Even though it's cheap gas, right? It's going to be a half the cost of a mixture of either this one or even this one. The reason people don't use it is like, oh wow, well it's half the cost or even less. And I could buy a cylinder that's this size for half the cost of this cylinder that's this size, and I get 5 times more gas out of here. So that makes it even more efficient, cost effective, right? Wrong. Because you save all your money here, and then everything downstream costs you more money. It requires you to run higher voltages in order to achieve the same arc, which means you work your power source harder, which means you're using more electricity. So now your electric bill is going to be higher. You get more spatter, regardless of what you do, whether you're short circuiting or globbing. If you're trying to spray, you're not. You're going to be globular anyway. But you are going to be producing a tremendous amount of spatter. How do you remove spatter? Well, now I'm buying more grinding discs, and I'm paying someone to get rid of all that spatter, and as soon as you start paying someone to do that, any savings that you ever have on that gas are negated by, it's huge, it is huge. So, but the physical cost of the gas, yes, it is less expensive. Now, the difference between the cost of this gas, and this one, so there are Argon CO2 mixes, right, are negligible. If a company is out there running 75-25 and you want to switch to 90-10, and the gas guy, your gas supplier, comes up to you and says, well, okay, well, yeah, that'd be great, we can do that, but your cost for your bottle is going to go from $120 to $150. You tell him, well, I'm going to go ask the next guy then. I'm going to go shop your price. Why? What's the number one cost of producing gas? How about what's the number one cost in producing anything? Come on, you know what? Number one cost, come on. Number one cost, what? Time, that's a good one. Number one cost? Labor, absolutely. Labor, which is time, right? You're paying someone to go and do this. That is your number one cost of producing anything, at least in this country. Might be different in other countries, but here, it's us. We cost the company more than anything else that they do. But luckily, they have to have us, which is great, okay? So, the difference between here and here is negligible. If you're using a certain amount, if you're just buying a bottle a year, well then, yeah, you're gonna be paying more for it. But if you're working for a company, which I assume all of you will be working for a company somewhere along the lines, and you happen to be in charge of sourcing the gas, you're probably sourcing it for maybe even a bulk tank that's outside. So if you have a bulk tank outside, guess what? They all have mixers on them. And that mixer, it's a simple thing as going out and dialing, I want this much argon and this much CO2. Simple as that. So the cost is not that big of a difference. Now, if it was going to go from $120 to $122, awesome. Sold, right? Bring me the 90-10. Because your benefits downstream are going to far outweigh it. It's also going to open it up to allow me to get into my pulse spray transfer, okay? Which that usually is what lights the fire for people to switch gases, is because they're changing the process. Now, when you get into the oxygen, you're going to pay more money for it. Why would you pay more money for argon oxygen? Oxygen is just as readily available as CO2. What's the number one cost of producing gas? Labor, right? No, that's the number one cost for doing anything, and it's because it requires more labor. They are all set up already to do argon and CO2, but to switch over to do argon oxygen, it's more labor intensive to get to there and to mix that and to make sure that it's being done correctly. So yes, you will pay more money for that, but it still shouldn't be a huge difference. All right, any questions on gas? I think that was a lot. This is just kind of general stuff right here. This is just adjusting voltage, so I won't worry with that. You probably covered that in class somewhere else. All right, so we went through short circuit, globular, spray, pulse spray, and RMD. Specifically, we want to focus on the RMD and the ProPulse or pulse in general. We'll go out there, we'll fire up the old continuum and probably the Delta Weld and probably the Pipeworks machine, kind of show you those. The Pipeworks and the continuum are the only ones that I have out there right now to do RMD, but the pulsing you can do with the Delta Weld and also any of the MPAs that are along that far along. Okay. So are there any questions about anything that we've covered? Any questions about Miller Electric or Hobart in general? You'd like to, because now's your chance. In the future, I'm going to give you just kind of if you have an opportunity, I don't think we're going to do it this go around when we come in to do interviews, but every 2 years, was anybody here at the info session we did? You were here, okay. Okay, good. We do that every 2 years, so